Very good morning to the students. As usual, let's start the lecture with the same prayer. Let us all seek guidance to the righteous from the Almighty, and also seek the knowledge which is beneficial to the society and mankind. With that, we'll start today's lecture on lactation curve, on the lactation cycle. See, earlier in our previous lecture, we have discussed about the lactation cycles that comprises of different phases: the early lactation, the late lactation, mid lactation, then dry off, or the dry period. That is a lactation cycle in case of animals. And the lactation curve is simply that represents the evolution over time of a herd's milk production during a specific lactation cycle. These lactation curves generally reach their peak yield after calving and then decreases steadily from then until drying up. So once there is a calving, the animal starts milking, the lactation, and it then reaches to a peak. In case of bovines, particularly by the day 60, or you can say like that 60, 70 days, or after 100 days, then it starts decreasing. There's a decline in the production till it dries off by the time, say, 300 days of lactation curve. So this lactation curve allows the evaluation of important milk production characteristics such as maximum production and persistence. So these lactation curves can be used for predicting the milk production in a herd, a maximum milk production, then their persistency. They also help in herd management, particularly in assessing cattle herds' nutritional and health status. These curves are also useful in predicting a cattle herd's total milk yield when only lactation cycles are observed. Only those early lactation cycle observations are known. Means when we're early in the lactation, we know those peak yields. We can calculate, we can predict the total milk yield in a herd. Areas for possible improvement can be quickly identified, leading to the management change aimed at increasing profitability. Then, if we move further, in temperate dairy systems, total milk yield for 300 days lactation can be estimated by multiplying the peak yield by 2. So it has been observed, if you know about the milk yield as a peak milk yield, then you can multiply it by 200 and it will give you the total milk yield for 300 days lactation cycle. That's the thumb rule. You multiply the peak yield by 200. So that's why we see if you manage a herd that its peak yield is maximum, even if you can increase a 1 kg of milk in a peak lactation or in a peak yield, that means you are increasing 200 kgs throughout that lactation cycle of an animal. So milk yield in pigs and rodents increases over time, such that greatest output is realized at weaning after 3 weeks. So in case of rodents, pigs, we'll see that this peak yield is almost at greatest at the time of the weaning. Means when those babies are taken away from the mother or this milking is stopped, they are weaned, they are taken away from the mother. That at that time you'll find that there's a greatest, milk yield in case of pigs and the rodents. Whereas in humans, guinea pigs and rabbits, peak of the yield is about halfway through a typical lactation cycle. So in case of humans and pigs and guinea pigs and rabbits, this peak will be halfway through a typical lactation cycle in this. Whereas in case of bovine, we have already discussed that its peak is between 60 days to 100 days. These changes are presumed to reflect change in the cell activity as well as balance between any change in cell number due to cell proliferation and death. So many statistical models have been used to describe the lactation curves. Typically in a dairy cow, you see that curve has the first phase, that's a rapid increase in the milk production until the maximum or peak production, the time at which peak occurs. That is followed by the second phase of decline in milk production, which is the longest phase. So typically in that dairy cow, we'll find once there is parturition, baby has taken the birth, the milk increase rapidly is that's exponentially until it reaches the maximum, or this you can say the maximum peak production by day 60, and then it declines slowly, and that is the second phase of decline in the milk production. And that the rate of that decrease of the milk yield in second phase is economically important and is referred as persistency. As I already discussed, that persistency, that's a rate basically at which this second phase or the decline in milk yield is there. So if it's not so rapid, if it's not, it's maintained a bit constantly, that means you're yielding a good milk yield, you're achieving good success in milk production. But if there is a say rapid decrease in the second phase of lactation, that's economically not good. It's poor condition. You find this is, if you find this is the typical lactation curve in case of the bovine, in case of say cattle, you'll find that whenever there is a say parturition has started, now milk yield is increasing rapidly. It's exponential increase in milk production till it reaches the maximum, say by day 60, and then it tries to get declined. And this is what we this if rate is not so rapid, or in other words this persistency, then you'll find a good if you find this say a bit not so rapid by day 300 of the lactation cycle, then you will have a good say milk yield. If there is a rapid decrease in it, then there is low milk yield. So this persistency is basically very, very important in case of cattle. And if you can improve this persistency, or if you can reduce the decrease in this second phase of lactation, second phase of this lactation curve, then you are going to increase the milk yield. So that's lactation persistency is the rate of decline in the production after the peak milk yield. Right, so the ability of lactating animal to maintain a more or less constant that milk yield in the declining phase of lactation, that is very, very important. And if you can manage that, that means you are managing good production from the animals. The inherent capacity of the animal for sustainable milk production, that's very important. If you can sustain that milk production by decreasing that say rate of decline, or increasing the persistency. The economy of the dairy animal depends large extent on the persistency of the lactation, as I have discussed. If you can maintain that persistency, if you can reduce that decrease rate of decline in the milk production in a second phase of that curve, that means you are yielding a good milk yield in case of animals. High persistence is associated with a slow rate of decline, whereas low persistence is associated with a rapid rate of decline in the milk yield. Normally, in general, we see that decline rate in the milk production is about 7% per month after the peak yield. And this is the optimum. If you can maintain this, decrease, the decline 7% per month, and that is reasonable, or that's manageable, and that's important. Not beyond that, if but it ranges somewhere between 3 to 4% per month in fully fed, lot fed cows, and to 12% or more per month in very poor fed cows. So if it is 12%, that means they are very poor cows. So in average, it should be between 7%. Then C, to maintain that persistency, in other words, what we name as galactopoiesis, how you can maintain that persistency, how you can maintain those animals their production at you can say sustained rate with say 7% or less than 7% decline in the second phase of lactational curve. So that is all what we name as lactopoiesis, how we can maintain that. So lactopoietic effect, so what are those growth factors or those hormones which are basically important in maintaining that persistency or the lactopoiesis? Growth hormone and BST, that's the bovine somatotropic hormone. They increase the milk production in lactating dairy cows, and that's a well-known fact. If you are injecting the BST or growth hormone, you'll find that the milk yield gets increased, and it's being used in case this strategy is being used in, say, developed countries, particularly in USA and Canada and many other countries. Whereas E2 and P4, that's estrogen and progesterone, that synergize with the prolactin and this growth hormone in mammary gland growth. You see, after this lactation, growth hormone and prolactin, they are very, very important hormones, which are very important in maintaining that galactopoiesis or the maintenance of the lactation. And so prolactin and the somatotropins, they are very, very important. Besides the E2, P4, they are there at the back. So prolactin and somatotropin may sensitize the mammary gland cells to effects of estrogen and progesterone. Mammary duct growth accomplished with estrogen growth hormone and the cortisol, whereas estrogen and growth hormone ductal mammogens, they are known as ductal mammogens, do not act directly on the duct but through the stroma-derived growth factors, that's the paracrine. So we have enough, those studies, and it has been demonstrated that the stromal tissue, not the ducts or the alveoli itself, but the stroma tissue, the extracellular matrix in mammary glands, the fat pads, what we name, that is very, very important, the stroma, because many of those hormones and the growth factors, they act via that stromal tissue, and they cause the ductal growth, or they cause, you can say, the epithelial growth. So stromal, not the epithelial estrogen receptors necessary for the ductal development. The mammary stroma strongly promotes ductal growth. Whereas growth hormone stimulates end bud growth through the stroma intermediary, that's the IGF-1. So growth hormone not directly acts on those, the buds and buds, or what you name the alveoli, but it acts through a stromal intermediary, again through the stromal tissue, and that produce the IGF, and that IGF then acts on those mammary glands or the duct system or the bud growth. And full lobulo-alveolar growth requires addition of progesterone and prolactin. Prolactin is very, very important in lobulo-alveolar growth along with the progesterone. Whereas in ductal growth, you'll find that estrogen is very important. So PRL, that's the prolactin, induces mammary gland development as well as lactogenesis. We have already discussed that prolactin is a lactating hormone. So this is the prolactin which maintains this galactopoiesis or maintains the lactation. PRL acts through the transcriptional factors STAT5A and STAT5B in the epithelial cell differentiation and milk protein gene expression. So PRL actually acts on the gene level, and it is one of the important, the hormone for epithelial cell differentiation or its multiplication, and then protein gene expression. So these are very important. This STAT5 is the principal and an obligate mediator of mammopoietic and lactogenic signaling. Mitogen, like insulin, like growth factors, TGF, they all cause cell proliferation, decrease apoptosis through PCL2 regulation. So if they increase the proliferation of the cells, of the epithelial cells or the secreting cells, that means, in other words, they have a galactopoietic effect, and they maintain the lactation. Whereas tumor necrosis factor alpha, TGF beta are cell death promoters, and they negatively regulate this. whereas evidence implicates transforming growth factor as the primary local inhibitor of growth ductal elongation and lateral branching. Again, a negative factor there. Mastitis, very important condition of the mammary gland, inflammation of the mammary gland due to many reasons, maybe the disease condition, maybe bacterial, maybe many other things there. Many other diseases that affect the mammary gland. So that mastitis negatively affects the cell proliferation and promotes the cell death through necrosis or apoptosis. So this is how you'll find that in detailed, the mechanism through which mostly the growth hormone and then say PRL and IGF, insulin, how they act on this mammary gland cells and the production of milk. You find that growth hormone, you have say receptors for growth hormone, you have receptors for prolactin, they act through JAK, STAT5 signaling. They increase the milk production gene expressions. They also increase, the mitogenesis of these epithelial cells or the proliferation of the epithelial cells. And they see growth hormone via, stromal cells. They act and they produce the IGFs, and then IGFs, you see here, again coming from here, IGFs and insulin, they act through cell survival, cell proliferation. That's very important in galactogenesis or other galactopoiesis. So cell proliferation is very, very important. Cell survival is very important to maintain that lactation during the lactation cycle. Then estrogen, progesterone, and cortisols. This is how these hormones and the growth factors, they all together act on these epithelial cells, their proliferation, their survival, and decreasing their apoptosis, decreasing their cell death, increasing their survivability, increasing their cell proliferation, increasing their, say, gene expressions and their secretory activities, thus maintaining the galactopoiesis, which is rather very important for, as a herd management system. Then after the lactation has been there, the lactation peak has been there, then it has come to an end. That's a dry period for involution. Means now the animal dries off. It's not that for whole this lactation cycle, the animal is lactating. You have a lactation period that will span from early lactation, mid lactation, late lactation. Then it will enter into the dry period, or what we name as involution. And this involution or dry period, it's also very, very important in the lactational cycle. In the pregnant animals, the mammary gland requires a non-lactating or a dry period prior to the parturition, means to the next parturition to optimize milk production in the subsequent lactation. The period is called as dry period. So it is very, very important to make the animal dry before next calving, before next lactation. So it includes the time between halting of the milk removal, that's a milk stasis, and subsequent calving. Dry period of 6 to 8 weeks for dairy cows is generally thought to be optimum for health, fertility, and milk production. Roughly, we take 8 weeks, 6 to 8 weeks. That's it should be a managemental strategy in the dairy farms to dry off the animals 6 to 8 weeks before the calving or before the next lactation. So dry period provides mammary gland an opportunity to revitalize and regenerate the secretory tissue for next lactation. Drying off the lactating animals that sets in the adult involution and transition from a dry period to the lactation is very critical phase in the reproductive cycle of dairy cows. Drying off is characterized by absence of teat stimulation and adder emptying that triggers the mammary gland to regress. So drying off is when you want to dry off an animal, just say don't milk it. And it should not be that you withdraw the milking abruptly, but you see, if you are milking thrice a day, then make it only twice. And if you are twice milking a day animal, then make it only once a day for a few days. Then if you are milking, say 10 liters, say for few days, make it only 8. Try to keep some milk in the udder itself, then the next 6, and then slowly, gradually, till you make the animal to dry off, so that it doesn't produce now more milk, or you are not milking the animal. So absence of teeth, say this stimulation, and then say intramammary pressure gets increased. Since you have absence of teeth stimulation is there, no milking is there, so intramammary pressure that is there, that decreases the milk synthesis. It has been established in case of the goats and maybe in the bovines, that one of that can say a low molecular weight protein is there. That's a FIL, that's a feedback inhibitor of lactation in goats, and serotonin in case of bovines have been believed to be involved in the evolution of the udder. So when you stop in this, when you stop the milk in the animal, FIL increases there, and pressure also increases there, and then this causes stoppage of milk synthesis, or it reduces the synthesis of the milk, and then also the extensive apoptosis in the mammary epithelial cells is observed during involution and detachment of the epithelial cells. Necrosis of this apoptotic epithelial cells, phagocytosis of cellular debris, and for fat droplets mainly by the macrophages and enzymatically degraded in the heterosomes, removal of the protein granules from the milk by digestion of the vacuoles by all lysozymes, invasion of adipose tissue into parenchyma, myoepithelial cells remain intact. One of the important things is there during involution. If you find that during involution, most of these epithelial cells, they get denuded, they get apoptotic, they get then vanished, and even that stromal tissue that gets reduced. But the important thing is that myoepithelial cells remain intact. They doesn't get abolished, or they doesn't get removed. So though increase in leukocytes in involution tissue, no inflammatory reaction has been observed during the involution in the dry period. The removal of a portion of the mammary epithelium is there obvious in case of animals, in case of bovines. Then you'll find that the activation of different proteases and an increase in the permeability of tight junctions between epithelial cells. These changes happen during this involution, during this drying period of the animal. There is those permeability of tight junctions, they get lost. The tight junctions get lost, there is increased permeability, different proteases, they get activated, replacement of progenitor cells that are responsible for expanding and maintaining the number of mammary secretory cells. So so epithelial cells that have been removed, that has gone apoptosis, there is replacement of progenitor cells, which take care of the new epithelial cells being produced for the next lactation. These changes are very prominent in rodents, and in ruminants, these changes are less pronounced. Whereas the relative proportion of the epithelial and stroma tissue is markedly changed, the epithelial area does not vary much during involution in bovines. This active involution is fully initiated within 2 days after the cessation of milking, and seems to last approximately 21 days in cow, during which period the remodeling process is completed. The composition of milk is greatly modified after cessation of the milk in the dairy ruminants. These modifications are the consequences of the reduced activity of epithelial cells, the action of protease plasmin in the milk, and the increase in the tight junction permeability. So in that case, lactose, milk fats, caseins, alpha-lactalbumin, beta-lactalglobulin, they decline rapidly, and lactoferrin is increased, that get upregulated. During involution, the concentration of different proteins of the blood origin, such as lactoferrin, BSA, Ig, is increased. And they do increase in sodium, then and decrease in the potassium, reduction of milk citrate concentration. They are all observed, and they are most probably due to the this permeability, increased permeability, or due to the this tight junction, say loss of tight junctions. Recruitment of immune cells, leukocytes, that increase rapidly in the bovine. The neutrophils, macrophages, they are predominant immune cells, plasminogen PA activities, they are greatly enhanced during this mammary gland involution. Matrix metaproteinases such as MMP1, MMP2, MMP14, and MMP19, they are all upregulated during involution in cattle. Then they are involved in the degradation of the extra matrix and the basement membrane output. Both whole animal and half-udder model studies show that the proliferation of mammary epithelial cells was greatly depressed before parturition in the absence of a dry period. So that's important. That dry period is very, very important before next parturition. Otherwise, you won't find a good lactation during next lactation period. If you won't give rest to the mammary gland, or you won't give that a period or dry period or involution period to the mammary gland where it is remodeled, its epithelial cells are being replaced and replenished, and many other machinery is changed there and makes the udder ready for next lactation. So dry period is very, very important. Is there any strategy to hasten the involution process would be beneficial to the farmers in terms of profitability and to dry cows in terms of health? Short dry period extends the lactation before drying off, thus giving the additional milk. If you can reduce, if you have a strategies to reduce this dry period, say of 8 weeks, below 8 weeks, then you can, of course, increase the milk yield per animal, but it should never be less than 14 days. Because it has been observed, if this, in case of the bovines, if this dry period is less than 14 days, then the milk yield in the subsequent lactation is reduced. So it's then recommended that at least your animal should have a dry period at least of 45 days to 60 days. That's important if you want to have a good lactation in next cycle. For that, you have many strategies. A common strategy is that you restrict the feeding some days before this drying off. Cows are milking intermittently and fed only hay. Then estradiol injections have been used to induce rapid decline in the milk production before drying off, as well as history of milk composition change after drying off. Similarly, prolactin inhibition could be used as a management tool to facilitate drying off. So we know that dopamine is basically the inhibitor of PRL. So if you have agonistics of dopamine, if you can use the agonists of dopamine, they will inhibit the PRL, and if PRL is inhibited, that will accelerate drying off. So cell proliferation was lower and apoptosis was greater in the mammary glands, mammary tissue of those which have been treated with the agonists of dopamine, maybe the quinabolide or maybe the cabergoline. They are all agonists of dopamine. If you use them, you are hastening the involution. These can be strategies, or a very important strategy can be a short 4-day photo period that's less than 8 hours during drying off, has been shown to have a positive effect on milk yield in subsequent lactation. If you can put the animals in the dry off period in establishments where photo period is less than, or daylight is only 8 hours, not more than that, then you'll find that this lactation, subsequent lactation, milk yield is increased by 10 to 15%. Even you can use now the automated systems, the artificial intelligence for taking the animals to the dry off period. You'll find these, in case of drying off, you'll find that, these tight junctions, these are epithelial cells, these are stromal cells, these are myoepithelial cells. And then you see these are dying of cells here. This is loss of these those tight junctions. It happens there in case of involution, not in lactating mammary glands. So when this weaning, you'll find that then these tight junctions, they are lost, and the apoptotic cells are being more and more there. See, dorcapathine and this STAT3, then cathepsin, or you can say caspases, they get activated, and then the program death is there. We'll find again here after this drying off, early in LIF will be increased, then its receptors will be increased, death receptors will be increased, LIF receptors will get increased. You'll find, and ultimately you'll find these are here, those apoptotic cells, they will get increased. These are almost the dying cells here. Say these are all dying cells. You'll find this whole afterwards during that drying period, this will increase, MMPs will increase, dead cells will be there. You'll find those tissues will be coming, adipose tissues will be established, and then tight junctions will be lost, and this is what we name as involution. And so this is, I think this is sufficient for the day. With that, I take the leave. Will be again next lecture with some other things. I mean, probably with some lactation, synthesis of milk constituents. Thank you. Thanks.